All right, let's look at the last circuit, circuit number 5. This is the NMOS, officially called the common source amplifier. So here we're going to look at this circuit not for its merits as a logic inverter, but as an amplifier like you did in Lab 8 last week. So let's look at the values here. What are we given? 500 ohms for RD, no load, 10 volts. It says 5 volts on the schematic, and then we have a MOSFET model here. Let me go ahead and copy that. Okay, put the model in here. We're going to get rid of the units. I think this is going to cause problems here. So we'll get rid of the units. The 2.0 volts is fine. All right, so let's get our schematic up here. Take a look. So we have VI, which is going from the gate to ground, and it is going to be a sine wave with an offset, which is TBD. So I'm going to do, let's go ahead and put TBD here for a moment. The amplitude will then be 10 millivolts, and then the frequency we didn't say, but let's just say it's 100 hertz. Okay, then we have our MOSFET M1, and we might have to look up the pinout for that. So let's go to the PSpice reference. Let's go back home, look at analog devices, M for MOSFET, and here we have the drain, the gate, the source, and the substrate or bulk, and then the model. So drain, gate, source. Drain we'll call B, gate we'll call G, source is going to be 0, and the bulk is connected to the source, so that's also 0, and then our model is going to be 2 and 7000. Then we have an RD that connects up to the VDD supply, so that'll be from DD, that's for VDD, to the drain, and that will be 500 ohms. And lastly, we have our power supply from VDD to ground, which is 10 volts, not 5. We're going to run our simulation. So what we're going to do here is we're going to run 2 simulations. First, we need to find out what voltage, what offset we should apply here. So we can do it 2 ways. One way is we can just run a transient simulation, and let's see, the duration we should run for this is 100 hertz, so it has a period of 10 milliseconds. So let's do 80 milliseconds. That'd be 8 cycles. Let's go ahead and try to run this. I have an error, missing value here in the TBD. It doesn't like this, right? Obviously it doesn't like it. We never meant to run it with that. Get rid of that. Okay, so let's just say if it was 2 volts. Okay. Then it runs, and we can look at what VD. Now, this is a little confusing. We see it goes up to 10, it comes down to something very close to 10. We're trying to adjust this voltage so that we get 10 volts or 5 volts at V out. So a better way to do this is to actually specify I'm going to specify another value here called DC, and I'll say 1 volt. All right, now this, let me explain what's going on here. Depending on the type of analysis that you're doing, you can specify a voltage source, in this case, that's value. You can give it a value that is going to be used specifically for that particular simulation. So sine is always used for time domain simulation. DC will be used for a DC simulation, and we haven't done AC simulations yet, but I could also put an AC value here if I wanted to, and it would be used only for AC simulations. So what I want to do here, before running a transient simulation, I want to run a DC simulation where I'm going to be sweeping this voltage VI over a range of voltages and finding out when does the drain voltage go to 5 volts. So let's look up in the PSpice reference manual the DC analysis. So we're going to go to commands, we're going to go DC. Okay, the DC command performs a linear, logarithmic, or nested DC sweep analysis on the circuit. The DC sweep analysis calculates the circuit's bias point over a range of values for this particular variable that you're going to sweep. It can sweep it linearly, by octaves, by decades, or just using a list of values. Alright, we'll do a linear sweep. The syntax is .dc. Linear is optional. It's the default one, so you don't need to specify it. The sweep variable name, and then the start value and the end value and the increment. Okay, so let's see if we can do that. So it'd be .dc. I can put len, though it's not necessary. And then we'll say that when am I sweeping VI, I'm going to start from 0 volts. I'm going to go to 5 volts, and I'm going to do steps of 0. I know I'm not going to go to 5. Let's just go to 3 volts, and we'll say steps of 10 millivolts. Now notice I still have the transient simulation in here as well. So what will happen is when I run this, it runs both simulations, and then I get to choose which one I want to see the results for. So I'm going to click DC. And notice that now on the horizontal is not the time domain. I'm not simulating over time, because a DC simulation sweeps a particular variable and solves the operating point or the DC analysis for that circuit. So VI right now is not a sinusoid. VI is a DC voltage. I specified it to 1 volt, but because it is called out here in the DC sweep, the DC sweep command takes over this value, overwrites it with the value that it chooses as it steps from 0 to 3 volts here. So we're going to plot VD in this case. And this should look very much like a DC transfer characteristic for your NMOS inverter. That's precisely what we're seeing here. So I'm going to zoom in between 2 and 2.5 volts here. And I'm going to turn on the cursor, and then I'm going to move down along here until I'm at 5 volts approximately. You know, roughly speaking, we don't need to get there while we hit it. All right, 2.37 volts. 2.37 gets me 5 volts. Now it's probably 237 and change, but I'm only getting 2 digits of precision. Let's see here. We can set this to 4. Okay, 2.365. 2.365. So now we can go back and I can put 2.365 right here. Let me show you something that's really handy though. I can actually put a variable in here. And if I put it in curly brackets, I can just say VI offset. Call it whatever you want. And then we have a command called .param. And I'll put VI offset, and then I'll assign it the value 2.365. What's convenient about this is you can have a set of parameters down below your net list, and maybe as you change your simulation or are iterating on things, you just want to change these parameters, and you don't want to hunt through your net list to change all of these. Instead, you can just go to a parameter section and change them. What's even more powerful is if a particular parameter is used multiple times in the net list to affect the value of a particular component. That's convenient because one parameter can affect multiple components. It wasn't necessary here, but it is. I wanted to show it to you anyway. All right, so now let's run the simulation. And if we run the transient, now I should see the output oscillating around 5 volts. There you go. So we have an average voltage that's about 5. Is it exactly 5? Well, let's check. So we can add average of V, or average X. We'll do average X of V of the drain, and my period is, it's 100 hertz, right? The sinusoidal signal coming in is 100 hertz, so that's a period of 10 milliseconds. So we'll put 10 milliseconds. And turn on my cursor, click on the average, and I see 5.02. So pretty close, pretty close. Now we're asked to, what's the question we're asked? Apply the DC voltage VI such that VO is equal to 5 volts. Report on the following. So we just looked at VGS. You can look at IDS, the operating current that results, and then now determine the small signal voltage gain at this operating point. So you're going to measure the VO peak to peak. And I'll let you do this, but you're essentially going to put your cursors on here and measure peak to peak, or you can use some of the other measurement techniques to do this. And now you've got your voltage gain if you look at this peak to peak relative to the peak to peak that we specified, which is not 10 millivolts, but 10 millivolts times 2, right? Because this is the peak value. Let's open up the simulation one more time. Which one is it? This guy here. Oh, come on. I'll close it, then I'll open it. There. Let's look at DC. So I can go Window, Display, oh, rats. See, this is where it would have been useful to save a probe display name. So I'll have to type this in again. VD. Yeah. And then let's do Control Y, add another axis, and I'll do I. Oh, I should show you this. If you want to look at the current through the MOSFET, because there's 3 terminals, you can't just say I of M1 like you can I of R1 and you know what current that is. With the MOSFET, or with any multiple terminal device, more than 2 terminals, you have to specify which terminal. So specifically for the transistors, like the MOSFET, you can type ID of M1, IG of M1, IS of M1. So if you forget, you'll see that up here. You see ID of M1, IG of M1, IS of M1. So you want ID of M1. And there you go. So here's the current. It starts out at 0, right, because the transistor's off. Once it starts turning on, it conducts some current. And we're asked, what is the current? What is the current when we supply the needed voltage at 3.6, whatever the value was, which produced VO equal to 5 volts. In other words, half of VDD. What is that current? So you can pull that off from this trace right here. Okay, I think we've covered everything, and I really hope that providing these videos will help you go through these simulations expediently. Particularly, I hope that it helps you to avoid pitfalls. I really hope that you don't just copy everything that I did without learning it. The whole point of doing this is so that you can be proficient. So later I can ask you, hey, go simulate this circuit, and I can expect that you'll know how to do it. So you're welcome to use all of the tips that I've provided, and even pause the video and look at my net list, but do try to understand it. Just don't copy by rote, or that's a pointless exercise. So, all right, thank you for watching.